Hello, everyone. We are going to discuss section 2.5 today. We're going back to using a PowerPoint for this because the book does actually a very good job overall in this section of highlighting what I think is important for you to know. However, there's one thing that I did want to bring in kind of as a reminder from a previous section. So we're using this format as opposed to scrolling through the textbook as we have for a few sections now. So let's go ahead and discuss the learning objectives, state the periodic law, and explain the organization of elements in the periodic table, predict the general properties of elements based on their location within the periodic table, and finally identify metals, nonmetals, and metalloids by their properties and/or location on the periodic table. So let's go ahead and get started with the periodic table. The periodic table is one of the major central organizing ideas in chemistry. We're showing here the original periodic table, which you might notice looks very different from the one you're probably somewhat familiar with and the one we'll be looking at shortly. But that's partly because they had different elements. They didn't know all of the elements then as we do now. So that's one reason. The other reason is they didn't actually know why it worked, just that it did work. So the person who gets credit for this is Dmitry Mendeleev, and you don't have to remember anyone's name for this course. But he was mainly a teaching professor. He wasn't doing a lot of research, and he was doing his work in a place not known for research. So it was a little bit surprising that he came up with such a big idea. And the whole reason why he came up with the periodic table was he wanted it to be easier for his students to learn chemistry by finding a way of organizing the elements that helped it to make sense so that it wasn't so hard for them. And the reason I say that is I think it's possible some of you have had maybe a high school teacher that wanted you to memorize the periodic table, and that is kind of defeats the whole point of even having it. The reason for the periodic table is so you don't have to memorize it. I carry around a periodic table with me. I guess now with cell phones we can get anything we want on the internet, but before cell phones, I've been carrying a periodic table around with me kind of wherever I go in case I need to look something up. So I don't have it memorized. I don't think that you need to have it memorized either. So here's the periodic table. And I wanted to point out a few things as we go through this. We've been alluding to this throughout the first two modules, and now we're going to actually talk about it a little bit. So the periodic table is showing us information about elements. So each of these little boxes on the periodic table is telling us a little bit about one of the elements. So each box is for one element. And we have basically 118 elements that are distinct elements that we have a little bit of information about each one of them here. And so we're going to zoom in on the first element and talk about the information that we have for that element from the periodic table, and you'd have similar information for other elements. So in the upper left corner is a number. That number is the atomic number. So each element has its own atomic number. And if you look at a periodic table, what you'll notice is we start with a 1, and then we go to a 2, 3, 4, etc. We just keep going up. Each element has a different atomic number. Okay, and so we've talked about this a little bit before, but the atomic number is defining the element. So if the atomic number changes, you have a different element. And that's, again, the atomic number, and we'll review this a bit more here shortly, is the number of protons, right? So the number of protons is defining the element. So each box will have a number, the atomic number. It will have a symbol. So instead of just saying, this is element 1 with 1 proton, we have a name for that. We call it hydrogen, and a symbol. We use the symbol H for hydrogen. So each of these elements, in addition to just having a number for the number of protons it has, we also have a symbol and a name. So on this periodic table, we have the symbol and the name. So H for hydrogen, H is the symbol, and the name is hydrogen. So both of those are on this periodic table. And then on this periodic table, there's another number underneath the symbol, and that number is the atomic mass. Okay, so for hydrogen, we're showing that's 1.008. So this number, we actually have talked about this in a previous module. The atomic mass is the average of all of the isotopes of that element. So we even, I think, referred specifically to hydrogen and talked about we have 3 isotopes of hydrogen. One of them has an atomic or has a mass number of 1, one has a mass number of 2, one has a mass number of 3. And if we take the average of all of those based on their percent abundance, we end up with 1.008, because most of them have an atomic number of 1, or have both an atomic number and a mass number of 1. So this is in this case, the atomic number and atomic mass are very close. So be aware of that. I did want to highlight something with that, however, because this is a point of confusion for many people as they're first learning about the periodic table. So that number from the periodic table, the atomic mass, is not the same as the mass number. Okay, the mass number is for a particular isotope. So when we looked at the mass numbers earlier, those are not numbers on the periodic table. You'll notice these are whole numbers because we're counting particles here, so protons and neutrons, whereas the atomic mass is an average of that kind of information. So just be aware of that when you talk about a mass number. The mass number itself is not on the periodic table. The number on the periodic table is the atomic mass. That's closest to being a mass number, but the atomic number. So atomic number is still counting particles, counting just protons, but the atomic mass is the average of the mass number. So make sure you know the difference between a mass number and the atomic mass. Okay, I want to go back. There's a few more things I want to mention on this periodic table in terms of some information that we're sharing here. So we already talked about the physical states, but I'll go ahead and mention that again. So the color of the symbol is telling us the physical state of that element at basically at room temperature. So most of them, will notice, have black lettering, and that indicates that they are a solid. A few of them have the blue coloring, so Br and Hg, that is indicating that they are liquids. And then several more have the red coloring, so up here and over here, that is indicating that those are gas in the gas phase. You don't have to memorize which ones are liquids or gases necessarily. We'll talk about a few things related to that. You should know a little bit about where to expect to see those, but that's something we'll talk as we talk about other things on the periodic table. Will hopefully make sense. The other thing I wanted to mention in terms of the color coding was this other idea of metals and nonmetals. So similar to the fact that most of the elements are solids, they are also mostly metals. And I know when I first heard about the periodic table, that was something that was very surprising to me, that most elements are metals, because um, I guess metals seem kind of boring in a way compared to all of the other things that can happen. But it turns out that that's the way it is, and we'll actually learn later why that is the way it is. And then only a small amount are nonmetals that we're showing up here. And then in between the metals and the nonmetals are what we call the metalloids, and we're showing those in this purple here. So let's talk about what we mean by metal and nonmetal, and then metalloid. So a metal is something that has the properties of conducting electricity very well, conducting heat very well, being very shiny, which is sometimes called luster, being easy to shape, and that could be called either malleable or ductile depending on the context. So conducts heat and electricity very well, is shiny, and is easily shaped. Those are properties that make something a metal. Later this semester, we will learn why metals have those properties, but for now, we'll just accept that they have those properties. For nonmetals, those are things that tend to not have those properties. So we're not saying exactly what properties they have instead, but the properties they have are not the properties of metals. They're the opposite of those properties. As an example, if you think of a piece of charcoal and think about trying to turn that into a wire, it wouldn't work very well because it would kind of crumble instead of forming the shape that you wanted it to form. And so nonmetals tend to have the opposite of those properties. You'll notice that many of the nonmetals are gases. So that is, in a way, tending towards the opposite of the properties of metals. And that's something we'll explore, again, a bit more later in the semester. So when I talk about not, you don't have to memorize which of the physical states we have. Just kind of see that most of basically all of the gases are in the non-metal portion. For the metalloids, these are elements that have either some properties are metals and some are nonmetals, or more commonly, many of these have the property that they can switch back and forth. So switch back and forth, what that means is that sometimes they are a metal, sometimes we get them to act like a metal, and sometimes we get them to act like a nonmetal. Now, this is a very convenient property because if you can get an element to act in different ways in different situations, then you can do some interesting things with that. Most of the metalloids are used in this way, but the one that is probably people are most familiar with is silicon. So you might think of Silicon Valley and other things related to that as being things that are important for computers, cell phones, are basically these microchips. And the idea there is that you can, using a metalloid, you can either turn on or off the ability to conduct electricity. So if you can make it something that you can turn it on or off like that, so act like a metal and conduct electricity, then act like a non-metal and not conduct electricity, then you can use that as a basis for making very efficient, very small computing systems. So metalloids are, even though there's not very many of them, are very important for the kinds of life we're accustomed to today when we are not removed from an electronic device for very long. I wanted to talk a little bit about the organization of the periodic table. And this is something we'll continue to explore in the coming sections of this module. So the reason why the periodic table works is because it's very predictive of the properties of elements. You can think of it as sort of a matrix where you have two things going on. You have, as we mentioned, the mass or the atomic numbers increase as you go across. An interesting thing is they didn't know about atomic numbers when they actually first made the periodic table. They used mass numbers or atomic masses instead. But it works for the most part. So that's one thing. The other thing is as you go down, you also have something, and that is the chemical properties. So we call these the groups of the periodic table. So the horizontal columns are the groups. So the first group are called the alkali metals. They have very similar properties. They are very reactive, especially these are the metals that if you throw them in water, they explode. So they all have that property. The second group are called the alkaline earth metals. They are also very reactive in kind of a similar way. Then we have this big chunk of things we call transition metals, and there are 10 columns here. You'll notice that they're a little bit depressed, so we have a bunch here, and then we're skipping two of the rows to have these down here. So these are the transition metals. These are all metals, and they have often very similar properties to each other. And we'll talk about those properties a bit going forward. And then we have this section where it kind of goes back up to sort of normal again in terms of the lack of depression. And then we have a few more groups. And then some of your book is putting names to these. I'm not going to have you remember all of the names. I'm just going to have you remember the last two. So the halogens are group 17. They have properties of being very reactive. And then the very last group of the periodic table, the very last column, are called the noble gases. They have the properties of being very non-reactive, unlike other elements that we've called out as being very reactive. Noble gases are very non-reactive. And then finally, if we take the first two groups and the last six groups, we call these the main group elements. So the ones that are kind of elevated above the transition metals. We also have these ones that are kind of down below, and these are sometimes called the inner transition metals. And the first one are called the lanthanides. The second one are called the actinides. And they're named after the first element within kind of that row. So lanthanum and actinium are how they get their names. You'll notice this arrow here. What's actually happening is that these elements actually fit into the periodic table. They're not just kind of floating around below it, but it makes it easier to fit it on a page if we arrange it in this way. I'm going to go back to the previous periodic table to look at this a bit more so we can see that we go 56, 57, 55, 56, 57 through 71, and then back to 72. And then same thing down here. We have 88, 89, 90 through 102, and then back to 103. I know this is very difficult probably to read in terms of those numbers, but you can look those up in your textbook as well. So a little bit about that organization. And then you can see on this one, we are showing the group numbers here. So 1, 2, 3 through 12 are the transition. 13 through 18 are the remainder of those main group elements. And then again, 17, 18, 1, and 2 are the groups that I want you to remember the names of. I didn't mention this earlier, but the rows also have numbers. These are called the periods. So periods 1, 2, 3, 4, 5, 6, 7. The reason the word period is used for these is because we have properties that are repeating. So the period is when they repeat. So they're periodic properties. So we have, for example, lithium has a property. Um, Sodium has the same property. So period 2, period 3, 4, 5, 6. So how often has that property basically repeated itself? So that's kind of why the periodic table works, is we have those repeating properties. I wanted to talk a little bit about why, and we'll get into this more within the next section, why that happens, and it is related to basically the electrons. So here we're showing sodium in a sodium atom. So if we look on the periodic table, we would see that sodium has atomic number 11. That means it has 11 protons. We would also expect it then to have 11 electrons if it were a neutral atom. And then this particular atom we're showing has 12 neutrons. That's not that important for what we'll be looking at here. What often happens, though, is that the sodium will lose an electron. And it loses an electron, so it, instead of having 11, it has 10 electrons. And then because it still has 11 protons, it ends up with a positive charge. So 11 protons, 10 electrons, plus 1 charge. And that is something that everything within that first group of the periodic table will do the same thing. They will all tend to lose 1 electron very easily to form an ion with a +1 charge. And we'll learn why that is as we move forward through this module. So in terms of what they end up doing, again, don't worry too much about memorizing all of these right now. We'll talk a bit more about this in the next section. Group 1 will tend to be a +1. Group 2 will tend to be a +2. Noble gases tend to not react. Halogens tend to be a -1. The group 16, again, you don't have to know their names, will tend to be a -2. Group 15 will tend to be a -3. We don't often have a charge here. Aluminum in particular will tend to be a +3. And then we have a lot of variability over here. Okay, so you don't have to remember all of these. But this is something we'll explore a bit more in the next section. This regular pattern of ionic charges is one of the things that leads to the similar chemical properties within the periodic table. So that is it for this section. Feel free to move on to the next section.